Did somebody say, I need some more theorems? Because I got some angle side theorems coming your way in 3.7. It's going to be a good day when these theorems come your way. Woo woo! A little isosceles triangle theorem. Well, if AB is congruent to CB, then AC has to be congruent, then A has to be congruent to C, my angles, and vice versa. The way we write this down, if you've got the sides, then you get the angles. If you've got the angles, then you can get yourself some sides. Woo! Heck yeah, dog. If sides then angles, if angles then sides. That's what I like to say. We're going to use it in a proof today. You guys remember this proof from 3.6? We had that AD and CD were legs of the isosceles triangle. What do we know about AD and CD then? Definition isosceles, they are congruent. Hey, if my legs are congruent, what do I know about my base angles? They are congruent as well. My goodness, I think we just did that proof without drawing an auxiliary line in, without proving triangles congruent and having to use CPCTC. So I've got AD is congruent to CD, def, iso, triangle. And then we are done. Finna gonna be done. Angle A, congruent to angle C. If sides, then angles. Love this proof. Now I want you to notice something. These guys are both triangles that we drew. Okay? They are triangles. People try to use this all the time in things that are not triangles. This if sides then angles or angles then sides only works with triangles. I'll point that out when it comes up. But make sure you're only using this in triangles. Okay? Frequently misused in past years. All right, looks like we got ourselves a fun proof here. I've got so much given information, I'm going to need to jot some stuff down. I've got HK and JM congruent. I find that difficult to draw the congruent marks, so I'll just use brackets outside. I got GJ and JK, OK and JK. Ooh, what's going to happen there, guys? What's going to happen there? I've got 3 of the same congruent marks. I'm going to leave it like that. But if we want to link GJ and OK together, we can use transitive property. Substitution works too. I'm going to do trans. All right. Next we got GJ and OK are perpendicular to HM. What does that tell us? Oh, we got some right angles going on, but we do need to say that in the proof as well. I want to prove that FHM is isosceles. Well, in order to prove something is isosceles, an isosceles triangle, what do I need? I need myself some congruent sides. Okay, I need 2 congruent sides, then I can get isosceles. All right, let's see what we can do here. How can I get congruent sides? Well, maybe I can do a little CPCTC. I've got that new if angles then sides type deal, so if I can get some angles congruent, I can get some sides congruent. All right, we got a couple options here. So let's see here. I've got these 2 little triangles on the outside. If we're going the congruent triangle route, I have a feeling I'm going with that. Okay? Maybe I could draw in an auxiliary line with an auxiliary point from F. I'm not going to go that route right now. Let's work with what we got first, and then we can hit the panic button if needed. I've got GJ and OK congruent by transitive property, if I so please. I've got right angles. That's good. Do I have anything else? Oh, I've got HK and JM congruent. And you know what? If I were to subtract, hold up here, if I were to subtract JK from both of those, that would leave me with HJ and KM congruent. Looky what we have here. GJ and OK, I can say those are congruent in my proof. Right angles, which we know are congruent. Sides, congruent from subtraction property. Side, angle, side. Side, angle, side. I've got congruent triangles. What can I get from there? H and M. Not the store, but the angles. If those are congruent, if angles then sides, tells me that these are congruent. Woo! My goodness, that is a lot. Let's put this thing together. It's going to take a little bit. So let's see what we got here. I'm going to move this up even a little bit more to get some room. Alrighty, so I've got my given. And then let's see here. GJ, that was one of the early ones we said. GJ is congruent to OK, either transitive or substitution. We're only linking two things together, so either one works. I like to use transitive when I'm linking together congruent statements because then I can do 2, 3, 4, 5 congruent statements. Doesn't matter. All right. Next one. I know that HJ is congruent to KM. Subtraction property. Okay, now I got that perpendicularity that I want to deal with from this guy here, right? So I've got angle, I'm just going to mark them 1 and 2. So we've got angle 1 and angle 2 are right angles by the definition of perpendicular. And because I know I'm going to be doing side angle side and not like a hypotenuse leg right angle, I've got to prove angle 1 congruent to angle 2. I know because I've looked ahead in my proof that I'm doing side angle side. So I do need to say these guys are congruent. All right angles are congruent. Then I've got myself congruent triangles. Triangle HJG congruent to triangle MKO. And that was side angle side. Make sure your congruent statements are correct. I always write down one of them, and then I ooh, there's a lovely voice crack. I'm gonna keep that in there. I could edit it out, but I'm okay with it. Once I have one of them in, I follow the other one. Okay, I'm double check those, make sure it all lines up. MK lines up with HJ. Angle K, or the angle with vertex K lines up with the angle with vertex J, so on and so forth. All right, I've got enough there. Let's keep it moving. Angle H is congruent to angle M by CPCTC. And lastly, oh, not quite. Almost done. I can get my sides congruent. FH is congruent to FM by if angles, then sides. And lastly, but not leastly, triangle FHM is an isosceles triangle. I'm going to move this down. Definition, iso, triangle. Woo! Man, I feel like I need a nap after that proof. That was lengthy, to say the least. All right, but a wonderfully exciting proof that you will think about for years to come. And just to reflect back on this, once again, our middle point, our checkpoint is that those congruent triangles, and that'll become a common trend here in a lot of our triangle-based proofs, okay? That kind of becomes like our middle step, not necessarily exact middle, but it's a good checkpoint. Okay, what triangles should I prove to be congruent so I can get some other information here in this proof? And so it's like you're almost like a halfway point, okay? Fun stuff. Oh my goodness, we have a proof, and there's no diagram, there's no given, just says to prove something. Let's read this sentence, shall we, from left to right, top to bottom. Prove the bisector of the vertex angle of an isosceles triangle is also the median to the base. My voice cracked once again. I wish I brought my water in here as I was planning to record 2 videos, and I am parched. But that's okay. I'll leave it in there. I'm okay with it. So basically what I have here is a statement in which I can get myself a given and a proof, and it really helps to also have a diagram. So I'm going to draw up a lovely diagram over here. A triangle, that is absolutely terrible. Let me try that one again. I'm going to draw myself an isosceles triangle, and then I have an angle bisector. So it's an angle A, B, C, and we'll call this guy D. And it says that the bisector of the vertex angle of an isosceles triangle, so in my given, I've got triangle ABC is an isosceles triangle. I've also got that AD bisects angle CAB. And what do I want to prove? Well, I'm going to prove that it's the median to the base. So prove AD is a median. Okay. Well, it's not so bad. Now that I've got all that, let's see if we can write this bad boy up. You know what I'm saying? That sounds delightful. Just delightful. Okay. Let's do this. Well, if I've got an isosceles triangle, I know that my legs are congruent, right? And I've also got an angle bisector, so I know I got some congruent angles. I'm going to jump ahead and say, if I'm trying to prove that AD is a median, what do I need to get right before that? I've got the little flow chart thingy going on I think we've talked about. Well, if I want to get to a median, I need a midpoint first. And if I want a midpoint, I'm going to need some congruent segments. How am I going to get some congruent segments? Well, if I want CD to be congruent to DB, I'm going to need some congruent triangles and CPCTC, right? Okay, well, I've already got a pair of sides, a pair of angles. What do I know about AD? It's congruent to itself. I could use that. What do I know about angle C and angle B? Well, I could use that too if I wanted, or one of them. I can get those two angles congruent by if sides then angles. So really we have a couple versions of this proof we could do with only really a slight variation. But once I've got those, my triangles are congruent, and then I can go through my median phase. All right, let's do this. Let's write this thing up. I've got my first step, given. Second step. Let's see here. We've got, how about, let's make this angle 1 and angle 2. Angle 1 is congruent to angle 2, definition, bisect. Let's go with step 3 now. AC is congruent to AB. Definition, iso triangle. Now here's the option. Either you can do reflexive property, which would lead to a side angle side triangle proof, or we can do if sides then angles. I'm going to do that. Angle C is congruent to angle B. If sides, then angles. That way I can use my new theorem because that's fun. It's always fun to use new things, right? That would mean that I'm going to have triangle CAD is congruent to triangle BAD by angle, side, angle. Step 6. How about a little CPCTC? I've got my flowy charty going down here. Got my flow going, flowing through the math proof. We can get some CPCTC going, right? Get some congruent segments. So CD and DB are congruent by CPCTC. And we got 7. Well, that would mean that D's midpoint, right? D, midpoint. Definition, midpoint. Okay. Let's see if I can move this whole thing up. All right, I can. Step number 8. If I've got a midpoint, what do I have? A median. AD is a median. Definition, median. America. Awesome. That was some exciting, wonderful stuff. And once again, children, we might notice our middle step, or right around the middle, not necessarily always exactly in the middle, but our general middle kind of checkpointy step, congruent triangles. CPCTC from there. Not every proof will follow this, but a lot of the ones that we're dealing with right now, that's kind of the phase we are in right now, okay? Alrighty, our wonderful angle side theorem about triangles, their angles, their sides, the relationship between the two of them. Let's say for fun that C is my smallest angle. What do you think might be across from it? That side right there. Do you think it's going to be the smallest, the medium size, the largest? Well, if it's across from the smallest angle, small. It's going to be across from the smallest side, small. How about, say that B is my medium-sized angle. What do you think is going to be across from that? Well, if this guy is my medium, then this is going to be my medium. And last, if this is my largest side, that's three of them, very much overlapping on one another. If that's my largest, what do you think is going to be across from it? Largest, large, large. So let's take a look at this inequality statement that we have down at the bottom. It says if AC is greater than AB, then that means that angle B is greater than angle C, which is exactly what we've basically stated here. So if this guy is bigger than this guy, then the opposite angle, opposite of this is B, the opposite angle is bigger than the opposite angle of the other one. Okay? So you can get that from like a relative size of sides and angles that have a relationship with one another. Let's apply it in a problem. So I'm told here that AC, segment AC, the length of segment AC is greater than the length of segment AB. What I like to do is I like to just notate it with a tick mark, just for my own notes, really. AC, I'm going to put 2. AB, I'm going to put 1. They aren't congruent. AC is bigger. 2 tick marks makes me think that it's bigger. It's not an official thing, but that's just what I'm going to do. Looks like our angles floated away, so these little guys right here and here, they needed to get back in that spot. All right. It says the measure of angle B is equal to 6x minus 45, and C is 15 plus x. Okay, let me jot those down in there. Let's say 6x minus 45 and 15 plus x. And we want to know the restrictions of the value of x. Well, let's think about that for a second. Restrictions generally mean, hey, we're dealing with inequalities. Is there an inequality that we could set up? Well, across from angle C is the small side, and across from angle B is the larger side. That would mean that 6x minus 45 should be bigger than 15 plus x, right? Yeah, that makes sense. So I know that 6x minus 45 has to be the bigger one, okay, because it's across from the bigger side. Let's solve this inequality then, shall we? I'm going to get the x's on one side, so 6x minus x is 5x is greater than, I'm going to add 45, that gives me 60. And if I divide by 5, x is greater than 12. Cool. Alrighty, so I know that x has to be greater than 12. Now let's think about this for a sec. Okay? Let's think about this. Could x get infinitely bigger? Like, can I keep going with x? Like, could I put in 1,000,000 for x? Well, would that make sense? 15 plus 1,000,000. 1,015. Can I have that as a degree measure in a triangle? Heck no. If I'm talking about angles here, I got to have an upper bound as well as a lower bound. Obviously, I don't want to go negative, and if x is greater than 12, there's got to be some restriction above. So what's limiting me from just having whatever I want when I'm talking about the angles of a triangle? Well, how many degrees are in a triangle? 180 degrees, right? 180 degrees is the total for all the angles of a triangle. Well, I got to have something for angle A, so we got to set up another inequality that involves that. I know, oops, I'm going to do this. I know that 6x minus 45, this angle plus this angle, need to be less than 180, because if they're equal to 180, I have nothing for my angle A up here. We got to leave something for our homie, angle A, right? So I got to be less than that. Let's solve. 6 and 1 gives me 7x minus 30. When I combine those, I get 180. 7x is less than 210 when I add 30, so x is less than 30. So these are my restrictions. X is greater than 12 and it's less than 30. You could even write it out as a compound inequality with x in the middle. X is greater than 12, less than 30, or you can list them both individually with an and between. I know it's a weird concept or thing to think about, but make sure you think through these problems. If you're dealing with angles, you can't just have as big of an angle as you want. Can you get as big of a side as you want? Yes, you can. But you can't just have as big of an angle as you want, okay? So if we have two angles we're dealing with, they got to be under, the sum of them has to be under 180 because we got to have something left over for the third angle. If you're finding restrictions when you're dealing with sides, sky's the limit for the sides. You can have as big of a triangle as you want, all right? You don't have to have an upper bound there. Whew, that was fun. Well, that concludes Chapter 3, children. Chapter 3 is a wrap. Got a quiz, review, test. All right, make sure you check online for the quiz. Checklist. Do it. There'll be some practice problems on there as well. Tear it up on that quiz. Tear it up on the test. America.